Hello guys, I will talk about the example in 4 parts. First of all, I will give you a brief introduction about the data and how to optimize the data. Secondly, I will talk about how to pick different features in the data. When I'm saying the word feature, I mean those independent variables that we need to predict our binary data. And then I will run a Poisson regression test as well as a logistic regression test, and then I will compile those two tests. Next, I will introduce you to the robust Poisson regression, which is to get robust standard errors and then to improve our predictions. Later, I will compile the results with our Poisson regression model, and then finally, we can find the confidence intervals as well as to draw some useful conclusions. Alright everyone, let's take a look at our data first. The data is called PIMA. It's a TXT file. I will give you a link in my description so that you can download it by yourself. Let's first look at the data. The data is about someone's health information, as well as about the test results if that person has diabetes or not. By running the code names, we can see that there are 8 categories in our data. And we can also use head to have a preview about our data. We can say that the last column is the thing that we want to predict, the test whether a person will have diabetes or not. Obviously, it is a binary data because it's positive and negative. Other columns, some of columns are like number of pregnancies and age. Those are countable data. And some other data like glucose, diastolic, those are continuous data. So here, our first step is to use dummy variables to replace our test results. From the code, if the test result is positive, we will replace it by 1, otherwise it will be 0. Also, we can see that from the head, some of those data are missing, like in insulin, those NA, and in triceps, those NA represents that the value is missing. So I'm writing the code to check how many missing values are they, and also in next line, I want to know that there are missing percentages. So by running the code, we can see that there are like 200 something are missing from triceps, and nearly 400 data are missing in insulin. And in percentage, almost half of insulin data is missing. Almost 1/3 of the triceps are also missing. Generally speaking, for data that are missing like those much, we will not use as features to predict our results. But for those data that are missing, some of them, we can replace them by each column's mean. So, for example, like the glucose data, there are 5 of them are missing. So basically here I'm saying that for all data in glucose, if there is a variable that is missing, and then it will be replaced by its mean. The same thing applies to diastolic and BMI. And next, we can start to choose the features that used to predict our binary results. First of all, let's run fit 1. The GLM here stands for General Linear Model. Basically, it tells or tests if there is a relationship between one dependent variable and some other independent variables. And here we choose diabetes as our binary result, 1 and 0, glucose as our independent variable, and family is kind of like the method that we're using. Here we use the Poisson regression method, and they take log as our estimation. And the second feed is also the same thing, but I add one extra independent variable, which is diastolic. So the ANOVA here tells us that if our features are useful or not. For example, here, the glucose feature, It has a very small p-value, but for the diastolic, it has a rather large p-value. So we can say that the beta for diastolic might be 0. So it is possible that we can drop this feature. And for the next feature, because the diastolic is possible to be dropped, so we add the BMI as our second beta. Again, we use the Poisson regression test. And then I also add the third feature as diastolic in our fit 3. And let's first take a look at the fit 3. We can see that the p-value for glucose and the BMI are small enough, but for diastolic, because the p-value is rather large, so we can say that the beta of diastolic could possibly be 0, which means that feature is not very proper. And also we can use ANOVA to compare that if extra features are necessary or not. So for example, like the feature 1 and feature 3 here, we're trying to see that other than the glucose, if BMI and diastolic are necessary to be our predictors, because they also have very small p-value, so they are possible. But here we're trying to test if the diastolic is possible to be an extra feature. But here again we see that the p-value is rather large, so I will just use the glucose and the BMI to be our main features. So just to make you see the Poisson regression more clear, I recode them and name it as fit Poisson with 2 features that we select, which is glucose and BMI. And then I fit another logistic regression. And so again, we use general linear model, but here the family will be binomial because we want to use the logistic regression method. And the link here is logic, which means it's logistic. And then we will try to see the results. So the results here, we can see all of them are within the range of 0 and 1. That makes sense because what we want to predict is the probability that a person might have diabetes or not. For example, the first patient for the Poisson regression method, he or she might have 46% chance to have a disease. And for the logistic regression method, the patient has nearly 60% chance to have the diabetes. And for the second patient, for the Poisson regression method, he or she only has 11% chance to have the disease, while in binomial as well as the logistic regression method, he or she will only has 6% chance to have the disease. The summary function here doesn't give us a lot of useful information. It just, as usual, gives us the intersections as well as beta 1 and beta 2. However, for example, for Poisson regression, the intersection negative 4.7 is meaningless here because we used the log transformation, which means what we really want is e to the power of negative 4.7. It has to be a probability that within the range of 0 and 1. The same thing for the logistic regression, because here we even use logistic regression transfer method, which means the negative 8 here is actually the log of p divided by 1 minus p. So we need to solve for p to get the real value that we want. And for the confidence interval, it's the same situation. However, here what can really tell us is that the range of confidence interval. So for the Poisson regression method, we can see there is a gap of 1.4 something, and for the binomial as well as logistic regression method, it has a gap of 2.6 something. So, which means for the logistic regression method, it's more inaccurate because it has a rather large gap between the confidence intervals other than the Poisson regression method, which has a smaller one. So after compiling the confidence interval of Poisson regression and the logistic regression, we will say that the Poisson regression is somehow more useful or more accurate. And then we can start to compare that the Poisson regression and the robustic Poisson regression. First of all, we need to import those two libraries. The library sandwich, do you remember in previous videos, we have a very long mass calculation and the matrix looks like a sandwich? Basically, the sandwich here is to help us to do the calculation to replace the variance-covariance matrix into that matrix. And the LM test library here is to allow us basically to still use the Poisson regression method, but with replacing the variance-covariance matrix into that sandwich variance. We will call our robust Poisson regression method as robust, and then we can see what our robust coefficients are. So again, the coefficient we get here is the log coefficient, which means we need to do e to the power of those coefficients to get the real values. So we can also do exponential robust. So the intercepting here is meaningless because unless if a person is dead, this will never happen. But for glucose, it means that given that BMI as a constant, one extra unit of glucose for one person will give that person nearly the extra 1.8% chance to get diabetes. For the BMI, it's the same thing, given that glucose as a constant. If a person have one more unit of BMI, he or she might have the extra 4% chance to get diabetes. And next, I will also give the actually coefficient for Poisson regression test. And here I wrote a function. Basically, it just gives out the exponential of everything. So let's compare with the robust regression method. So we can see here they have very, very close results. However, there exists an obvious difference between the Poisson regression method and the robust Poisson method. We can see that for the robust Poisson method, the standard errors are smaller than those in Poisson regression method. And those differences could also lead difference for their confidence intervals. So next we will look at the confidence intervals for Poisson method as well as for the robust Poisson method. The robust Poisson method has to calculate its confidence interval by hand. So here are the results. We can see that the confidence interval for robust Poisson method that has a smaller gap than those in Poisson regression method. We can see, for example, the CI glucose here compared with the regression method. It has a smaller gap as well as for the BMI. They also have a smaller gap that less than 3, but the BMI in Poisson regression method, the gap is larger than 3. So, which means in another way that we can say the robust Poisson regression method did increase our accuracy compared with Poisson regression method. Alright guys, those are all of the examples. Thanks for watching.